All right, Chem 115 for 2020, September 28th, Monday lecture. Okay, at the end of Friday's lecture, we talked about solubility rules. Solubility rules is a set of generalized rules as a tool for us to determine whether an ionic compound is soluble or insoluble when you're dealing with solution chemistry problems. Okay, and we talk about two rules already, and number one and number two. These two are the two soluble rules. Okay, now the ions mentioned in these two rules. Okay, altogether there should be 6 positive ions and 6 negative ions. Positive ions are the group 1A metal cations, so lithium, sodium, potassium, rubidium, and cesium. Okay, and ammonium. Okay, these 6 positive ions. Okay, no matter what kind of negative ion they're combined together with. Okay, you see one of these guys as your positive ion for your compound, even if the negative ion is something that you've never seen before. You can take it for granted that this ionic compound that you have is a soluble ionic compound, which means when it's in a solution chemical problem, a solution chemical reaction, that compound should fully dissociate 100% into free ions. Okay, and rule number 2 is very similar. The only difference is we're dealing with 6 negative ions. Okay, and there are nitrate ions, nitride ions, chlorate ions, perchlorate ions, acetate ions. So and bicarbonate ions. Okay, so if you see a chemical compound, let's say I see something like this. Okay, manganese nitrate, and I don't have a rule discussing manganese. This is a transition metal. I don't know the solubility of manganese ions, but it doesn't matter. You see your nitrate ion right there. You know this compound is a soluble ionic compound, and if it's in a solution chemical reaction, this thing would fully break down into manganese ion and 2 nitrate ion. Okay, how do I know that manganese here has a 2+ charge? Well, nitrate has -1 charge, and you have 2 of them in the formula. Manganese got to be +2 to offset and make the chemical compound neutral. All right, so you see these 12 ions, 6 positive, 6 negative. The compound involved is always a strong electrolyte, a soluble salt. Okay, now number 3. Okay, chloride ion, bromide ion, and iodide ion compounds. Okay, are soluble except when combined with three positive ions, and they're silver, lead 2+, and mercury 1 ion. Okay, so number 3 is still kind of a soluble rule, but this is a soluble rule with exception. Now, these first 2 are soluble rules, no exception. You see these guys, then you can put your stamp on soluble. Okay, no matter what the other positive or negative ion is. Now, for chloride, bromide, and iodide, okay, mostly they make soluble ionic compounds. So majority of the compound that you see containing ionic compound containing chloride ion, containing bromide ion, containing iodide ion, okay, would be put into the strong electrolyte soluble salt category. Okay, the only exception happens with for those three ions are these three positive ions. Okay, so three positive ions, three negative ions. How many possible combinations do you have? Well, 3 times 3, 9 combinations. Okay, so what do you mean here? I'm telling you that silver chloride, silver bromide, silver iodide, lead chloride, lead bromide, lead iodide, mercury 1 chloride, mercury 1 bromide, and mercury 1 iodide. Are insoluble. Okay. Now, if these guys shows up on the product side of a chemical reaction, solution chemical reaction, then they are precipitates. Okay. Now, other chlorides, other bromides, other iodides, you see them, break them down, they dissociate 100%. These 9 guys won't. All right, so I do want to specifically talk about the mercury 1 plus, mercury 1 ion. Okay, now. All right, the reason that I called this mercury 1, okay, despite the fact it has a +2 charge here, is that you notice this also has a subscript. Okay, now, and this ion, metal ion here, you can actually view it as a kind of a polyatomic ion. Now, between the two mercury atoms, okay, there is actually covalent bond. Okay, and together these two shows a +2 charge to the outside word, and of course, now if you put the a charge on each of them, each mercury is only losing 1 electron. Together, the two of them lost 2 electrons, and that's the +2 charge. And this one is kind of special because if you look at these 3 formulas, you don't normally see ionic compound formula like this. Okay, remember NaCl? You would never write it as Na2Cl2. Okay, because we said before, okay, ionic compounds are in 3-dimensional array. They don't make molecules, and when they're in 3-dimensional array, we're going to take the smallest whole number ratio. Okay, 2 to 2 is 1 to 1, so use 1 to 1. And then, now if that's the case, why did you use 2 to 2 here? Why didn't you do this as HgCl? Well, this time HgCl would be wrong. Why? Because again, we just told you that this is a special polyatomic ion. Okay? These two do stay together. They're bonded together. Now remember when we were talking about sodium chloride, we said, well, your 2 sodium ions wouldn't stay together. So you can't write it this way because they both have positive charge. They hate each other. They push each other away. This 2 mercury have no choice but staying together. They're bonded together. Okay? So although this look like a 2 to 2 ratio, this is essentially a 1 to 2 ratio for these three compounds. It's 1 Hg2 2 plus ion and 2 chloride, bromide, or iodide ion. It's essentially a 1 to 2 ratio. So this doesn't conflict with our idea of ionic compound should have the smallest whole number ratio. You're still 1 to 2 is still the smallest whole number ratio. Okay, now it's not a 2 to 2 ratio here. Okay, but this is kind of a side knowledge nugget that you might get confused on later on when you read this. I just want to explain it clear. Okay, but coming back to our main point, rule number 3 of solubility rules is chloride, bromide, iodide compounds are soluble except when they're combining with these 3 positive ions. Rule number 4 is also a soluble with exception rule. And this time we deal with only one negative ion. Okay, now sulfate ions, okay, compounds are soluble except when combined, so same wording, with this time 6 positive ions. 3 you already are familiar with: silver ion, lead ion, and mercury 1 ion. And then calcium ion, strontium ion, and barium ion. Now, how do I remember these 3? Well, if you know your strong bases, you already know these 3 ions. Okay, the 5 positive ions in group 1 and these 3 positive ions together, 8 of them, gave you the 8 strong bases. Their hydroxides are the 8 strong bases. So you already know this group. And you already know this group from rule number 3. And all 6 of them, okay, makes sulfate ions precipitate, makes sulfate ion insoluble. So silver sulfate, Ag2SO4, lead sulfate, mercury 1 sulfate, calcium sulfate, strontium sulfate, and barium sulfate. These are the 6 sulfates that's insoluble. Or you can say if they're made in a solution chemical reaction on the product side, they're going to be precipitates. All right, now rule number 5. So rule number 1 and 2 are soluble rules. Rule number 2, 3, and 4 are soluble with exception rules. Okay, rule number 5 and 6 are mostly insoluble rules. So the wording here is oxide ions and hydroxide ions, their compounds are insoluble except when combined with group 1A and calcium, strontium, and barium ions. Okay, so you are having a whole bunch of ions again. I'm going to have to remember. Group 1A, you said is 5 ions. These 3 3 more, so 8 ions with combining with 2 negative ions, 16 possibilities. I need to remember all of that. It's too much. Not really. Okay? Like I said on rule number 4, okay, you already know this group. Okay? You know them from the strong base. Well, look at the 8 negative positive ions here. Okay? And look at hydroxide. If you already know your 8 strong base, which you really should, okay, because you're going to see them a bunch on your exam too. Okay, if you already know your strong bases, you got nothing to memorize here. Okay, of course, these guys together with hydroxide are soluble. Okay, yeah, of course they're soluble. These are the 8 strong bases. Okay, this also answers your question when we were talking about strong bases. Like, what about something like, copper hydroxide, magnesium hydroxide? Why aren't they strong bases? Simple. Okay, their hydroxides are insoluble, and if it cannot dissolve in water, can it give you a strong base solution? Of course not. Okay. So you know your strong base, you know the ions involved in here. Now, why did you involve oxygen? Generally speaking, okay, oxygen compounds, okay. Why do you involve oxide, not oxygen? Now, generally speaking, oxides, okay, metal oxides are mostly insoluble. Okay, yeah, and majority of the rocks on Earth, okay, are made of, especially, different mines, okay, not coal mine. Coal is basically carbon, okay, but different kind of iron minerals, copper minerals, all those rocks, okay, they're different metal oxides combination, okay, they don't dissolve, okay, they're insoluble. And even these guys, the group 1A and calcium, strontium, and barium oxides, when you put them into water, they're not exactly dissolving. Now, of course, let me give you an example, okay, sodium oxide, okay. Sodium oxide is such a reactive solid, reactive compound, that the moment you put it into water, okay, don't expect this thing to go into Na plus and O2 negative. Okay? That doesn't happen. So what does happen? Now, going into water, you're going to end up with 2 sodium ion. Okay, and that oxygen, so 2 sodium comes off. That oxygen is going to, due to water, okay, it's going to take 1 hydrogen away from the water. Okay, oxide is -2, take 1 H plus in, so that's why you get an OH negative. And if you take 1 H plus from water, what you got left? You have another hydroxide. So these guys are going to react with water. Group 1A metal oxides are going to react with water and still get strong base. Okay, and similar for calcium, strontium, and barium. These guys can react with water and make calcium ion and 2 hydroxide ion. Okay. This is why these 8 metal oxides are called base anhydrides. Okay, because you put in water to these oxides, they're going to react, they're going to disappear, they're going to dissolve, and they're going to give you a strong base solution. Okay, so really rule number 5, solubility rule number 5 is all about the strong base. Okay, hydroxides are strong base, and oxides, when you put them into water, are going to end up in strong base. Okay, and if you compare this to rule number 1, you do notice that, like, where in group 1 you said anything with group 1A and also ammonium should be soluble. What about ammonium with hydroxide or ammonium with oxide? Sorry, wrong place. Well, ammonium and oxide won't make a compound, period. Okay, these two just don't get together. Okay, ammonium and hydroxide could get together. Okay, but when these two get together, now, the result is not a ionic compound. Now, we don't normally write it as this. You could, okay, but we don't normally write it as this because this thing now, can quickly break down into regular ammonia with 3 hydrogen and a water molecule. Okay, so whenever you have ammonia and hydroxide getting together, you ended up getting a molecular compound. It's not exactly the full 100% dissociation that we were discussing before, and that's why it's not included in here. Okay, now, so that's rule number 5. Now, rule number 6. Rule number 6 is kind of a everything else rule. Okay, the ions that we didn't talk about here, ionic compounds containing F, fluoride ion, sulfite ion, carbonate ion, phosphate ion, chromate ion, are insoluble except when combined with group 1A or ammonium ion. Okay, now, do you mean that I need to memorize another rule involving a whole bunch of negative ions? Remember a whole bunch of negative ions, and then the rule and the positive ion? Again, you don't have to memorize it like that. And like I said, this is what we call the everything else rule in Chem 115. Okay, all the other negative ions that's not showing up in rule 2 through 5, okay, you can put them into this category. You run into a negative ion that you don't remember seeing in rule 2, 3, 4, 5. It belongs here. You can assume that it's one of these, okay? And you can assume that their compounds are insoluble, but if you already have rule number 1 remembered, rule number 1 is these guys are soluble with anything, okay? You can't go contradict that. So except for the rule 1, 6 positive ions, all the other negative ions combined with all the other positive ions to produce you insoluble ionic compound. How about that? Yeah. So now, again, solubility rules is a set of rules that's generalized for to simplify our understanding of the material here in Chem 115. Okay? Now, it didn't take us to go very far in the chemistry path to ditch it. Okay? A lot of you would move on to Chem 116. By the time we get into Chem 116, we're going to tell you that, okay, we don't, at some point we're not using solubility rules anymore because there's more complicated, there's more in-depth understanding that we would have on these ionic compounds. Okay, but right now, I'd rather have you understood this as a black and white, soluble and insoluble. Okay, applying the rules. And now for your exam too, you absolutely need to know these 6 rules of solubility like the back of your hand. Okay, or better than that. No, you just need to know them. And not only you need to know them, you need to be able to look at a compound and quickly make a judgment which compound is soluble, which compound is insoluble, which ones can I dissociate into ions, which ones can I not dissociate into ions. Okay, because you're going to do a lot of that. Like even for, let's say, think about it, for a solution chemical concept equation problem. Okay, let's say I gave you 5 chemical equations and ask you which one is a precipitation reaction. What do you need to look at? You need to look at least 10 products, 2 for each choices, and judge on their solubility. Okay, and it definitely cannot take you, a question like that definitely shouldn't take you 5 minutes, 10 minutes to look at every single compound and trying to recall the solubility rules in your mind. You got to be able to look at those compounds and then just instantly write on it, or write down soluble, insoluble, soluble, soluble, insoluble, insoluble. Okay, now, so your understanding of solubility rules gotta be to that level for you to use it, in your exam, and without wasting too much of your time. And I don't like memorizing contents in a chemistry class because I firmly believe this is more about understanding than memorizing. But there are things like you have to memorize. Now, going through a science class like this, and this is probably very high on that very short memorizing list. Know your solubility rules. Okay? Now, so now that we know how to predict products of of the reaction between 2 electrolytes, how to break down, okay, those molecular formula of the compound into a full, from a molecular equation to a full ionic equation, how to cancel the spectator ions in full ionic equation to get net ionic equation. Okay, now let's discuss a few different reactions. They're all double displacement reactions. Okay, but during the process of predicting products and predicting full ionic equation, predicting net ionic equation, there are lots of things that you need to be careful about. Otherwise, you might end up getting a problem or getting a wrong answer in an exam. So let's see a few examples. Now, first of all, does all double displacement reaction happen? Okay, what do you mean? Well, it looks to me like you can, from what we did so far, you can combine any 2 electrolytes, and as long as they don't contain the same ions, okay, you can always exchange partner and get something different for a molecular equation. does that mean those reactions happen? Every single one of those reactions that you can write, you can predict, always happen? Not necessarily. Okay, so let's take a look at this next example here. Okay. NaNO3 react with Cu SO4. Okay, we want you to predict possible product, get the full ionic equation, and get the net ionic equation, and identify the possible identify the possible spectator ions. All right, so let's do that. First of all, you got to exchange partner. Okay, after a couple lectures, you should be fairly familiar with this. Okay, sodium is +1, nitrate is -1, sulfate is -2. That means your copper is +2. All right, so sodium gonna go with sulfate, copper is gonna go with nitrate. So copper, nitrate, +2, -1. So I better have 2 of these. Okay, and then sodium and sulfate +1 and -2, I better have 2 of those. And then, of course, make sure your equation is balanced. You put your 2 here. Then, okay, I got a molecular equation. 2 electrolytes, exchange partner, and making me 2 more. 2 different electrolytes. All right, so what's the full ionic equation? Okay, let's go. Anything containing sodium or nitrate are going to be soluble, so 2 positive ions, 2 negative polyatomic ions. Okay, copper sulfate rule number 4 is about sulfate. Sulfates are soluble except with silver, lead, mercury, calcium, barium, strontium. Copper is not one of them, so soluble. Yeah. Sulfate ion and copper ion. Yeah. And then, so left side, 2 strong electrolytes, 2 soluble salts, all broken down. On the right side, okay, anything containing nitrate is soluble. So copper ion soluble, 100% dissociation, copper ion, 2 nitrogen ion. Anything containing sodium is soluble, so 2 sodium ion and sulfate ion. So 2 strong electrolyte on the right side. Now, so you got your full ionic equation. What are your spectator ions? Let's go. 2 sodium, 2 sodium, 2 nitrate, 2 nitrate, 2 sulfate, copper. Oops. I canceled every single one of the 4 ions. All ions, in this case, are spectator ions. What does that mean? Well, if all ions are canceled as spectator ions, do you have a net ionic equation? Of course not. No net ionic equation. Well, no net ionic equation means what? Remember when we first introduced net ionic equation in the last lecture, we said net ionic equation is the real chemistry. Remember in that neutralization reaction, we said H plus and OH negative are going to neutralize each other and turn into water molecule. That's the real chemistry in the neutralization reaction. No net ionic equation means what? No chemistry. No reaction. Nothing happened. But I did write a chemical equation. That chemical equation doesn't mean anything. Because you don't have these compounds binded together in the solution. You don't. Once you put them into water in solution, they're free ions. On the left side, you have 2 free ions, 4 free ions. On the right, you have the same 4 free ions. Nobody found their soulmate. Well, no chemistry. Okay, so this should answer that question. Like, okay, does any 2 ionic electrolyte, okay, always come without common ions, without the same ions, always combine and make a chemical reaction? The answer is no. Okay, if you end up having 4 strong electrolytes, in reaction, then you can pretty safely count that as no chemical reaction at all. No. All right, so that's one example. Now, previous page. So ammonia and hydroxide, when they get together, gave you ammonia and water molecule. Here's another one. Okay. Sulfuric acid and calcium hydroxide. Oh, okay, that one's easy. Sulfuric acid is one of the 7 strong acids you told me. Okay, 100% dissociation and everything. Calcium hydroxide is one of those 8 strong bases you told me. Okay, 5 in group 1A, then calcium, strontium, barium. So 8 strong bases. Oh, strong acid, strong bases. Shouldn't the ionic equation be H plus OH negative equal to water molecule? Well, let's see. Yeah. So reaction, of course, is exchanging partner. H and OH getting together, calcium and sulfate get together. Okay, this is +1, this is +1, this is -2, this is +2, this is -1, so water, H and OH getting together, +1, -1, getting me water. And since I have two of each, that's going to give me 2 water. Calcium and sulfate, +2 and -2, perfectly together. Now, all right. So now, that is a neutralization reaction, and we can feel pretty safe to say that this is going to happen for sure. Not like our last example, no, because you did make something you can't dissociate. That's not a strong electrolyte there. Okay, so strong acid, 2H plus, SO4, strong base, calcium, hydroxide, 2 water, you can't break down water, and then calcium sulfate. If you quickly go, this is going to dissociate, you're wrong. Why? Well, rule number 4. Sulfates are soluble except when combined with what? Silver, lead, mercury 1, calcium, strontium, barium. Oh, calcium sulfate is an insoluble ionic compound. As a product in this reaction, this is actually a precipitate. That is your full ionic equation. Now, do you have any spectator ion in here? Is there anything on the 2 sides that's the same you can cancel? If you wrote it wrong, then you have calcium and you have sulfate you can cancel, right? Now, do you? Your calcium and sulfate got together. And they got out of the solution into this solid precipitate at the bottom of your beaker. Is that the same with your free-moving calcium ion and free-moving sulfate ion in the solution before this happens? Of course not. And if they're not the exact same, can you cancel? Of course you can't. So, no spectator ion in this reaction, and your full ionic is your net ionic equation for this reaction. Make sense? All right, now, one more. Here's another neutralization reaction, okay, happening between an acid and a base. A base. The base is a strong base. The acid, if you think about your seven strong acid list, phosphoric acid is not part of your 7 strong acids. Okay, so this is a weak acid. Now, first of all, let's predict products. That should be easy. Sodium is +1, hydroxide is -1, hydrogen is +1, you have 3 of them, phosphate is -3. Okay, so sodium is going to go together with phosphate, hydrogen is going to go together with hydroxide. Sodium, phosphate, +1, -3, so you're going to need 3 of those to offset the charge. Okay, and then hydrogen and hydroxide is going to make you water, and you're going to need 3 sodium hydroxide to satisfy the 3 sodium need, and also 3 hydroxide can work with those 3 H plus and give you 3 water. Okay, so I predicted my molecular equation pretty easily. Now, what about full ionic equation? Okay, so that's a strong base. Okay, easy. 100% dissociation means 3 sodium ion and 3 hydroxide ion. Okay, and this is an acid, so 3H plus, phosphate. Oops, you're wrong again. Okay, what do you mean? Like, there are acids, all acids are electrolytes and dissociate? Yes. Okay, all acids are electrolytes and dissociate. But only the strong acids dissociate 100%. Okay, so if this is one of those 7 strong acids, no doubt in your mind, okay, break it down into H plus ions and negative ions. But this is not. Okay, you have a weak acid here. So what should I do with my weak acid? Remember, weak acids have partial dissociation. Okay, and matter of fact, vast majority of your weak acid molecule, regardless what kind of weak acid you have, vast majority of your weak acid in a solution stays in the molecular form. Only a small portion of your molecules break down into ions. Okay, and that's why for all the weak acids, you have to keep in your reaction the chemical formula in the molecular form. Okay, you have to. Okay, because this is the main presence of your weak acid in the molecular form. Little bit of it dissociate into ions. Okay, now, and if you're wondering, well, if you say only a small portion of it dissociate, does that mean only a small portion of the ions are free and can get together, and then your reaction would never get to the end? You would never be able to consume the rest of your H3PO4? That's not the case. Okay, only a small portion of H3, the weak acid, can dissociate. Okay, the ones dissociate made the free ions, and these free ions will react with the strong base you have here. Well, after you consume these weak acid, these free ions made by the weak acid, okay, remember, weak acid in a solution, okay, always dissociate some. Once these hydrogen ions are consumed, okay, you don't have dissociated weak acid anymore. So This weak acid, the leftover weak acid molecules is going to dissociate a little bit more, small portion. And then those are going to be reacted, and then you're going to need to dissociate another small portion, so on and so forth. Eventually, this reaction still goes to the end. Okay? But when you're writing the chemical equation, you have to keep it in molecular form. And then, okay, anything contains sodium is soluble, so 3 sodium ion and a phosphate ion, you have to dissociate that. And water is a regular molecule, you can't dissociate that. All right. This is your full ionic equation. Okay? What about net ionic equation? Well, what are your spectate ions? Do you have any spectate ions here? Oh. Sodium is never going to find a soulmate. Okay? Matter of fact, none of those 12 ions in the first two rules is ever going to find a soulmate. And that's just the way it is. Okay? They're spectator ions. No. Well, I take that back. Like some of them, no, you're gonna see. No, ammonium, when it get together with hydroxide, it can still ended up being a weak electrolyte. And so sodium, no. Okay, let's just focus on sodium here. Sodium, no matter where it is always going to be a spectate ion. Okay? No. Because when it makes salt, it's soluble. When it makes base, it's strong base. Okay? No. It's always 100% dissociation for sodium. Anything contains sodium. Now, all right. So that's the full ionic. That's the spectator. And what you got left? So H3 PO4 plus 3 hydroxide producing phosphate ion and 3 water. That is your net ionic equation. Okay? Now. And now, remember, the weak acid, weak base, wherever they are, as long as they're in your equation, okay, you can't break it down. You can't dissociate it, okay? Here's another example having the weak acid or weak base on the product side, okay? Imagine that you have ammonium nitrate reacting with potassium hydroxide. Okay, so +1, -1, +1, -1, exchange partner. So KNO3, 101, and NH4OH. Well, remember that? If you go back to, so instead of writing that, ammonia and water molecule. Okay, now dissociate, 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 dissociate. Soluble salt with ammonium nitrate and strong base with potassium hydroxide. Soluble salt with potassium nitrate. Why? Because potassium and nitrate are both soluble ions. Potassium and nitrate plus ammonia and water. Nitrate cancel, potassium cancel. Oh, so NH4 plus react with hydroxide, produce ammonia and water. Molecular equation, full ionic equation, net ionic equation. So a conclusion you can come to at this point is that, let me generalize it for you, okay? For a double displacement reaction, to happen, okay, your reaction gotta contain, okay, as a product, either one, a precipitate or insoluble. If you made an insoluble ionic compound, okay, that means you're going to have a molecular formula or a formula unit you can't dissociate, which means they can't be canceled. And if they can't be canceled, you absolutely are going to have an anionic equation. So if you make a precipitate, okay, your reaction, double displacement reaction, is definitely going to happen. If you make a molecule or a molecular compound like water, like ammonia, and we'll probably talk about a couple more in the next class, okay? If you're making a molecular compound, then your reaction definitely is going to happen. If you're making a weak electrolyte, like a weak acid or a weak base, then remember we don't dissociate them, so your reaction definitely happens. And if you're not getting one of these things, and you have 4 strong electrolyte in your equation, you got no chemistry, everything is a spectator ion, everything cancels. We'll pick up from here on the next lecture.